Hello. Hi. How's it going? Um, I'm here again to continue working on Break It for the Game Boy. Um, Hopefully the stream is going to go okay. I'm a little bit groggy. I got up kind of early. It was a very beautiful day, so I decided to get up early and go for a hike here on beautiful Vancouver Island. So a little sleepy, but I think I can make it through an hour to an hour and a half of streaming and a little bit of coding. So yesterday we did a bunch of refactoring and just code cleanup and stuff like that to make the code base a little bit more comprehensible. I'm going to just pull up the game as is right now. So we've got a ball, it bounces around, and it can fall off the screen and die. And yesterday, at the end of the stream, what I wanted to do was fix this issue where if I'm holding down the launch button and then the ball falls off the screen, it just immediately launches. I want to make it, you have to actually press the launch button in order to launch it instead of just being able to hold it down. I started doing that, and I got a little bit hung up on some of the binary logic stuff required. So I gave it some thought after the stream, and I realized some things that I had been doing wrong. And I think the big thing that I'd been doing wrong is I was sort of trying to think imperatively. I was trying to think, well, these are my inputs. What are the logical operations I can do to get it to the output that I want? And I realized instead what I should do is I should try to think sort of more declaratively. I should try to think, what does it mean for a button to be pressed? And well, it means that last frame it was up, and this frame it's down. And that's it. That's really straightforward. And so I just need to apply that math to what we have. And some other stuff I realized is that this is a misnomer, really. This should be keys up rather than down, because that's how it works. That's how the Game Boy's input register works, and we're just duplicating that. So I'm going to mimic that in the naming, so that way the things are more clear. And that will require making some changes, but no big deal. I want to make sure I don't forget. I'm actually very likely to forget if I don't do this now. There's not one particularly good place for it. I want to make sure I call this an input. I'd forgotten to do that earlier. But then, so now that I've renamed keys down to keys up, it's like it's much more obvious what it means for when we're testing against it. Like when it's a 1, just by convention, that means that something is on. And so you can read it, you can be like, oh, well, we're testing keys up for a particular input. It's 1, that means the key is up. It's just a little clearer. And then that'll also make this logic easier to think about, because we actually will have last up. So we don't need to do anything to adjust this. And this frame down, we can get really easily just by taking the complement of keys up. So that just equals not keys up, basically. Or maybe that syntax is better. If you're familiar with C, this is the operation for inverting all the bits, which is extremely similar to, but subtly, you didn't need to do that, subtly different from that. So we do that to get the keys up, and then all we have to do is point HL to last up and against it, and bam, keys pressed is now in A. Sorry, keys pressed. Yeah, keys pressed is now in A, and we're done. No, sorry. I'm still not used to VS Code's column selection mode. It's super helpful, but it's just slightly weird sometimes. So having done that, we are going to need to go make some changes here because this refers to keys down rather than keys up. But we didn't change the semantics of it, so we just need to update the name, the variable name. We have to do the same thing in ball for the launching. Where is it? Keys down. Yeah, your keys up now. Although actually, we're going to change this to keys pressed. But let's make sure that this builds, and it does. Let's make sure I didn't break the input. So let's reload the ROM. I broke something for sure. Yeah. Oh, I think I got that backwards. Let me check this. Or forgot to save something. Either is possible. Input. We want to put that in there, not there. There we go. Okay, so that should fix that. Let's reload the ROM. Yeah, what went wrong there is I was initializing last up rather than keys up, and so then we would immediately try to read from keys up in the Game Boy. Well, BGB caught that bug, that access to uninitialized RAM, and threw an exception. Threw an exception in quotes. But yeah, so this is all working as it was before. And so now, let's make the next change that I want to make, which is use keys pressed here instead. And keys pressed, as the name suggests, will be 1 when the key is pressed. So when it's not 0, we want to launch the ball. So reload ROM, run. So we have to make sure this all still works. And now here's the moment of truth. I'm holding the button down, and you can see it's not launching the ball. And then I press it, and it launches the ball, which is exactly what I wanted. So this is awesome. These are the changes I wanted to make yesterday. So I'm going to just make some commits in Git. I might split this up into 2 commits just for the sake of clarity. So to do that, I use Git's patch mode. Yeah, so I'm not going to... One moment. Excuse me. I'm actually going to... Well... Let me try that again. So we're going to split that. We're going to edit this. And this is a lie. But I'm going to pretend that, like, for this commit, it's just going to be the renaming of the keys down variable to something that is, like, more appropriate and communicates better what exactly it does. So I'm not going to touch any of the logic. I'm going to split this up again. I'm not going to have this last step or this keys pressed. I'm just doing the rename. So don't need to touch any of that. I do need to touch this. But again, it's just the rename that I'm doing for this one commit. And this way, I can like go and look over my git commit history, and this commit will be doing one thing, and it'll be really obvious that it's correct. And that's as opposed to like if I just did one giant commit that included both the rename and also the keys press functionality, and also using the keys press functionality on the ball. Like that's going to be a much bigger commit. It's going to be much harder to read that and audit that and be sure that it's correct. So that's why I used git adds patch mode to very selectively describe the exact commit that I wanted to make. I'm going to actually do that as well for the remaining changes. I'm going to have one commit for implementing this keys pressed functionality to our input system, and then another commit to actually use that for launching the ball. So there we go. Cool. The next thing I wanted to try to do is, and this is a minor thing, but it could probably be put off until later, but it's nice and easy, so let's just get it done now, is there's going to be times when you're playing Breakout that, like, you know, you're going to be over here, the ball's going to be coming, and you're going to want to rush to get it, and it's going to be really frustrating that you don't have enough speed to get over there and hit it. So just like adding support for being able to move the paddle quickly, like a run button basically, should be nice and easy to do, and should also just make the game more fun to play. So what I'm going to do here is right now we have this handle input, and I'm actually going to rename this to just handle movement. So that way we don't need to touch it, and it just does the one thing. It detects if you're pressing left, it detects if you're pressing right, otherwise it stops the paddle. But then I'm going to have a handle input method or procedure that, I mean, it's what's going to invoke handle movement. And the next thing it's going to do is it's going to check to see if you are running. I'm going to just call it running, I guess. And so what we're going to do is we are going to get the keys that are up, and if you are what is it? It's input. I'm going to put it onto the B button. And if it's up, we don't do anything. If you're not pressing B, we don't do anything. If you are pressing B, I'm just going to do it's a little trick. I'm going to I'm just going to multiply the current velocity by 2. And to do that, you can actually just do a shift left. If you shift some bits left, I don't want to get into it too much, but like if you've got a binary number and you shift all the bits left, so if the first bit is a 1, you shift that left, so now the second bit is a 1. You put in a 0 on the right side and you push the left off the edge. That works as a multiplication by 2. So I'm just going to do that. And that way, if you are... is that going to work, though? Is that going to work? That would totally work if it was a 1-byte number, or if the Game Boy had 16-bit arithmetic, but it doesn't. So is that what I want to do? I'll do a 16-bit shift. That's fine. So to do a 16-bit shift, we first shift the least significant byte, and the shift left instruction will actually push the 8th bit, the most significant bit of the least significant byte. It'll push it into the carry register, or carry flag of the status register. And so then what we're going to do is we are going to, and I'm actually going to need to look this up to make sure that I get this right. One of these rotate instructions will then push, it'll do the shift left, but it'll push the carry bit into the least significant bit of what will be the most significant byte. And I believe the one that we want here is going to be RL. But I'm going to double check. And the best website for that is Z80Heaven. At least I find its instruction reference clear. Where is its instruction reference? Oh, instruction set. Yeah, here we go. So I believe RL is what we want. This is a 9-bit rotation to the left. The register's bits are shifted left. The carry value is put into the 0th bit of the register. So that's exactly what we want there. So we first get the least significant byte of the velocity. We shift it to the left, pushing the most significant bit into the carry bit of the status register. We then increment HL to point at the most significant byte of the velocity, and then we do this rotate, which does that left shift and slides the carry bit into the least significant bit of the most significant byte. I believe this should work. Because we reset the velocity every frame, this will always do the right thing. And just doing it this way is easier than like trying to somehow combine this. Like, oh, you're pressing B and you're pressing left. Then we set the velocity to this. Otherwise, we set the velocity to that. Like, doing lots of sort of branch-heavy operations in assembly language makes it just like you don't have any of the structured programming features. You don't have ifs and elses and loops. So anytime you have to do any of that, you kind of have to roll it by hand using branches and comparison instructions and things like that. And it just gets really nasty. So as much as possible, it's kind of, I think it's good to avoid those. This is like, honestly, this is true of any processor. Like nowadays, branching is so slow on modern processors because they're kind of designed to just pipeline everything. So even if you're programming a modern computer in assembly language, or even if not in assembly language, the principle still holds. As much branching as you can avoid as possible, the better. So let's see. After all that rambling, let's see if what I just did actually works. So we can move around. That launches. Yeah, you can see now, if I'm holding the button down, I can move very quickly. Which, in theory, like it adds more skill and depth to the game. So I think this is a nice improvement. So I'm just going to save that change now to Git. I called it running because, I mean, if we can imagine this is like tennis or squash or whatever, it is kind of like running if you were an actual person. The paddle doesn't have legs, so it's not really running, but you know, for lack of a better word, it's fine. Cool. Okay. So we are now in a position where we can start to actually add the bricks to the game. And we need to kind of think about how we are going to store the level data in memory. So a really it's wasteful, but it's probably the best way to do it, and it's probably the way that I'm going to do it, at least in memory. It's possible we want to store it in ROM in a different way, in like some sort of packed format, but in memory, because we're going to be doing lots and lots of collision detection against the bricks, we do want to make sure that we can do that really, really quickly. So the format that I'm proposing is just 1 byte for each possible brick, for each brick. And this is sort of like the key point here. 16 bytes per row. And the reason why this is key is because it's a little bit non-obvious. If we look at the Game Boy, and we look at I'm going to pop open this VRAM viewer so we can look at the screen. The Game Boy screen is 160 pixels across, which means that any given row could have, assuming that we've got 8 pixel wide blocks, which I think is a reasonable assumption. The most you'd ever really want, I mean, the most you could possibly have is 10. 10 blocks, and the most you'd ever reasonably want to have, because you probably, we actually might even want to make this even skinnier, but like we definitely want to have like some kind of border on the sides. Like we might even want to draw a border and then have like another pixel gap. So the most you would ever want at the is 8 blocks per row. And possibly even just like 6, if you want to get like super I don't know, fancy by having a border, or but the reason why I want 16 bytes per row is because that'll make it really, really fast to go from a row number to the particular offset into the map. So that means we're going to be wasting a bunch of space in memory, but that's okay. That means that we can take 1 and just do a multiplication by 16 to get like row 1. We multiply by 16. We're 16 bytes in, and that'll be the start of the second row. Similarly, we take a 2, we multiply by 16, we're at row 2. And the reason why multiplying by 16 is so fast is because the Game Boy processor has a swap instruction. And what the swap instruction does is it takes the contents of A, this 8-bit number, and it just swaps the 2 nibbles around. So we end up with this. Actually, let me make this clear. Let me just show you like that. So this nibble here goes over here. This nibble here goes over here. And in particular, we're never going to have a row number which is going to be more than 16, because that just like wouldn't fit on the screen at all. So just doing this swap operation, that shifts it left by 1, 2, 3, 4. And do you remember what I said before about how left shift is a multiplication by 2? Well, that means that we're multiplying by 2, and then 4, and then 8, and then 16. So this is a super, super fast way. It's 4 cycles. It's as fast as any instruction gets. And it's also, you know, it's nice and easy to read because it's just one instruction. So I really like this format as much as possible. I use, when I'm doing any sort of like 2D math or 2D array work on the Game Boy, I always try to make it at most, or I always try to make it exactly 16 elements across, and then at most 256 elements total. So at most 16 by 16. Because that just makes all of the math so much easier. You only ever need to do 8-bit arithmetic to index into it. It is definitely the way to go. So that's the format that we're going to use. The only other thing is that, well, I'm going to start with 8x8 bricks, but I think I'm actually going to switch to 8x4 eventually, just because 8-pixel bricks, like square bricks, just, it doesn't look great. It doesn't look the way that Arkanoid Breakout always looks. Like, let me get some screenshots of Alleyway on the Game Boy, which is like you can see these bricks are horizontally longer than they are tall. Like, that just looks better unless you get like more detailed, you know, more detailed stage layout. So eventually we're going to do that. For now, I'm going to start with 8x8 pixel bricks. Just for the sake of ease, and then hopefully retrofitting, you know, doubling the vertical resolution will be not too hard. So let's get started with that. So I'm gonna, eventually this is gonna go into its own separate module, but for now, I'm gonna call this stage, I guess, and I'm going to call it like the stage map, and let's see, how big should we make it? Make it potentially. Oh, 8 is a good number, so that'll be 128. And I'm going to bytes, and I'm going to make sure to align it 8 bits, because again, this is a way, this ensures that the first element in this array is at memory address 0, and the second element in the array is at memory address 1, or not, well, not 0, but the last. It ensures that no matter where it's allocated, it'll be at, like, you know, CA00 or 8300. The lower byte will always be 0, and that means that when we're constructing an address index into it, we don't need to do any addition at all. If we say, oh, we want to get the 50th entry in this array, we just set this to, you know, CA or whatever, and we set this to 50, and we're done. We don't need to add, like if this were at 1 and we wanted to get element 50, we need to do an addition. We need to add 1 to 50 to get 50. So that's what that alignment there is for. And it just makes this sort of stuff easier. Really, really important on the Game Boy. It's not just about like things being faster, although things being faster is great. It also saves you code space because you're no longer like ROM space, because you no longer need to have all these instructions to do additions on every single array lookup. It saves you like just the sort of visual difficulty of parsing the code. The shorter the code is, the less complicated the code is, the better, which is so important when you're programming an assembly language, when everything is like so hard to keep in your mind all the time. So I'm going to delete all this as well. So let's add here. Did I use mixed case for that? No. I really like capital letters for my 8-bit assembly languages and their instructions. I think that's a little weird. I think nowadays most people kind of prefer using lowercase letters, but something really, I don't know, like satisfying. It just feels really 8-bit to use lots of capital letters and stuff like that. It feels really retro, and that's what this is all about, right? We're retro programming. We might as well, you know, do things in a retro kind of way. So, what next? Next, I gotta emit the stage. And this is, you know, easy. This is just we clear A out, we set B the number of, you know, the size of it. We have HL point to the stage map. And then we do this just like a very standard clear loop. Okay, so and then the next thing that I want to do is I want to, not actually, this shouldn't really be a clear loop because we do need to, you know, actually load a level from ROM, but for now this is fine. I'm going to we'll call it BG tile data. And that's in ROM. And again, I'm going to do much like what I did for the ball or the paddle. Oh, I put all that in sprites, didn't I? Like just draw it using constants in the assembly language. So it's just easier. Yeah, these are just bricks, so very, very easy piece of cake. I'm going to write a little procedure to load this into video memory. I have, where do I have this? I have this configured here. The background tiles are at 8800. So that's that. Super, super straightforward. This is going to be 16 bytes. So we load that into B. And we write a little copy loop. So we get A from HL and increment HL. We write that to DE. We increment DE. We decrement B, so we count down. And as long as we're not 0, we loop, but once we hit 0, we're done. There, graphics loaded. I've got my procedure to load it. Let me just save and build and make sure that we have that. Ah, right. And so this is going to be tile number 80, or like minus 128. And that's just how the Game Boy does its map data. Tiles count from minus 128 to up to 127. So there we go. Perfect. Next, well, I suppose the next thing to do is to actually, instead of calling this init state, it's actually to define a stage. And this is, yeah, this is in ROM. We don't need to align it anywhere because we're just going to be copying it in. And we can actually, so it's 16 bytes per row. So, oh, sorry, this should be 80. I believe what we can do is we can just do that, and that'll define. Oh, no, let's not do that. And what I can actually do is I can use basically the same sort of, I think I can use some sort of, I need to learn my assembler a little bit better. It's got some nice features which like help make these constants. Yeah, I could define a tile map so that I can actually just write this as a character map. So I can write this as a string. What I'm going to do is I'm going to use push C and pop C. So what I'm going to do here is I'm going to say that a dot is 0. And a hash symbol, let's go with that, is 80. So then what I'm going to be able to do is I'm just going to be able to write, you know, dot dot hash hash. Just so I can like be really clear about how far along I am. I said I wanted these to be 8 rows tall, so VS Code, man. Okay, so there, this is our first stage layout. So I'm actually going to load that. Instead of doing this clear loop, I'm going to load that. So this is like another example here of why using these aligned arrays is great. I can save 4 cycles by doing inc E and just incrementing E instead of inc DE. And I know this will always be okay because I know that E from 0 to 120 is from the map is from 0 to 128 on E, and D is always fixed. So this will be fine. So I'm going to do that. We've initialized the stage. Then I need to draw the stage. That's the next thing I need to do. This is going to work pretty similarly. It's still basically going to be a copy loop, but at least for now, with the 8x8 blocks. So where did it? Yeah, the map is at 9800. So it's going to work basically the same way. We're going to set the destination to 9800. We're going to, and if I wanted to, I could be a little bit more, like I said, there's lots of padding. I think the technical term for when you've got a buffer which has like a certain amount of space, which is what you actually want to use, but then the rows continue on for the sake of like making pointer arithmetic faster, easier. I think you talk about the width of the array and then the stride of the array. So the stride of the array is 16. So if I wanted to, I could just go over the width and then go to the next row and ignore the pixels that are in between, or the tiles that are in between the width and the stride. But it's just faster and easier to just do a dumb copy. It doesn't hurt anyone, and so let's just do the dumb copy. And I'm trying to think. Let me pop open the VDAM viewer again. Oh, I had it there. Yes. So right, each row here is actually, oh, well, this is a thing though. Actually, I take back everything I just said. Ignore what I just said. Unless I wanted to make the map 32 pixels or tiles wide, which is the actual width of the Game Boy screen, which I don't want to do, I will need to do some thinking about things. So oh, whoops. Oh, I don't want to touch this. I want to fix this in the draw part. So instead of doing that, it's 8 rows. And then we'll say it's, I'm going to say that it is, so I have to do math anyways. We'll say that it's 8, the width is 8, and then the stride is 16. Is 8 pixels? Yeah, 8 tiles should be wide enough. 1, 2, 3, 4, 5, 6, 7, 8. No, it's not. 9, 10. I have been in my head thinking about 16 pixel tiles. That's why I've been doing math wrong. Tiles are 8 pixels wide. When you're making lots of times when you're making games, you do want to use 16 pixel meta tiles, but tiles are 8 pixels wide. I'm so sorry. I've been telling lies, terrible lies. So the Game Boy screen width is actually 20 tiles wide. 16 is perfect. That gives us 2 pixels on the, or 2 tiles on the left, 2 tiles on the right. Perfect. So for the sake of optimization, we know that when we're drawing columns, the again, we can just increment E, because if you look at the addresses here of any given row, it never wraps around on the higher bit, or higher byte, I mean. Because each row is 32 tiles wide, 32 bytes, divides evenly into 64 or 256. So there's just never any point on any given row where the higher byte increments, but it's always at row boundaries. So because of that, when we're doing this copy loop, we can just increment E. So then once we're done drawing a row, as we've done here, what we need to do is we need to, and I'm actually going to, right, what I'm going to do is I'm actually going to start it at 98, 20, 22, maybe even 23, 98, 42. What we need to do is that once we're done, we need to then do some math to go from like here, we're going to copy our 16 tiles across. We're doing it here. Now we need to do some math to get over here in our destination. And there's probably faster ways to do this than what I'm about to do, but I like this for clarity's sake. We push the destination onto the stack. We pop the destination off. So that's going to bring us right back to where we started drawing the row, and then we just add 20. Hex 20, which is 32. And then we sorry. And then once we've done that, we're adding an 8-bit number to a 16-bit number, so we need to do a little bit of work with the carry flag and stuff like that. So what we do is we say, did that addition cause a carry? Well, if it didn't, just skip ahead. If it did cause a carry, let's increment D. And that's the fastest way on the Game Boy's processor to do this style of adding an 8-bit number to a 16-bit number and handling the carry properly. Then, having done that, we decrement C, or sorry, this should be a C. Having done that, we decrement B, which is the row count. And if that's not 0, you go back up to draw a row, otherwise we're done. So if all goes according to plan here, what did I call it? I didn't call it stage, I just didn't give it a name. all goes according to plan here, we should have our first level loaded. And that's a big if. Oh, and it did not go according to plan. So, except it did, according to the. It went according to plan, according to the. Oh, I probably haven't set the background palette up yet. Yeah, that's the problem, I think. Let me go do that in init palettes as well. I believe the background palette is palette. No, not Game Boy. 47. Yeah, it's 47. So let's write the same palette that we're using for the sprites there. Reload on. Did that work? That still didn't work. Palette is correct now. The tiles are correct. Why can't I see the background? Huh. It did look like the tile needed to be fixed, but... Oh, do I not have the background on? I don't think you can disable the background, can you? You can. I need to enable the background. It's like, doing this is really interesting because I'm very self-conscious about it, since I'm in a way that I'm not if I'm just programming on my own. And I get to reflect a little bit more on my ignorance. And, you know, I have been hobby programming for the Game Boy most of my life, almost. Probably most of my life. I'm pretty sure I did some stuff with it when I was a teenager. And it's like, I should know stuff like this, but also, it's so easy to forget that, oh yeah, you have to set bit 1 on the display register in order to make sure the background appears. Did I? Oh God, if that wasn't it, I'm gonna go nuts. I'm gonna lose my cool. Because I feel like that has to be it. Yeah, there we go. Look at that. And of course, there's no collision detection yet, but we do have the background. And it's there, and we loaded it. And yeah, we're so close to having a real, actual breakout game. Pardon. Like I said at the beginning of the stream, I'm kind of sleepy. Late night, early morning. Great hike. You ever get a chance to come out to Vancouver Island, which you should, if at all possible, when possible. Obviously, right now, travel, bad idea. You ever get a chance to come out to Vancouver Island, the John God, what's the guy's name? I want to say John Deere, but that's not it. There's a provincial park here. John Dean, maybe? John Dean Provincial Park. That's where I went this morning, so it's embarrassing that I can't think of the name. But just stunning. Absolutely stunning. Highly recommend it. Spectacular. Just great views. Just like a perfect West Coast hike. All right. So I feel like that is perfect time to make a commit. So the next thing to do clearly is to break the bricks when the ball hits them. And I think today what I'm going to do is I'm going to get brick collision detection coded up. But I'm not going to actually break the bricks, because breaking the bricks is going to be a little bit tricky, because that's going to involve drawing to the screen while the screen is on, which we need to do in our VBlink handler. So that's going to be a whole thing. And instead of doing the whole thing, I'm going to just immediately crash the Game Boy when a collision is detected. And that's what we're going to get done for today, hopefully. Even that's a little ambitious. But I'm going to take a quick break. So just to get a drink of water, I'll be right back, and then we will get going with some collision detection. God. This is what I'm drinking, this delicious Perrier sparkling spring water that is peach flavored. It's like LaCroix, but I feel less like a Californian when I drink it. Like a New York fashion intern or something. But unfortunately, it does not have caffeine. You may be wondering why I just opened up an in-private window, and it's because I'm tired and not thinking, and I instinctively sat down at my computer and opened up an in-private window to go to Facebook, which I do in private in a futile and desperate attempt to preserve my anonymity when using it. But now is not the time to be checking Facebook. Now is the time to be coding for my adoring audience. Here we go. Ball. So, much like we did here, where we check the left collide, the right collide, now we're going to call check stage collide. Where's... Oh gosh, okay. Oof. I'm going to actually do that after updating the ball X and the ball Y. So that would be update ball moving. Yeah. Again, no, unfortunately. So this is real subtle, but I'm going to make couple of quick changes. First of all, I'm going to call the Y update first. And that's because if the ball collides with a brick, we want to during its motion, we want to prioritize the collision on the y-axis. I don't know if this matters. I'm clearly very tired. Not thinking. My thoughts are often muddled and confused, but now more than ever, I might just focus on doing the y, update ball y. We will need to do a collision check on the left and the right for the movement on the left and the right, and we're going to do that so that way, if like the ball is bouncing up the sides, we kind of do the right thing. We reflect left and right, but for now I'm going to focus on the y. There's probably going to be some horrible code duplication. We're gonna need to workshop this a little bit, but for now, this is fine. So what we're gonna do is we're gonna get the ball's position. We're gonna construct a pointer into the stage. So remember I said like the stage map is fixed because it's aligned on an 8-bit axis. So we just set the H to the constant, I like to call it a page, the page number, the high byte of the address. We're going to get the ball's Y position. We are going to we're now going to divide it by 8. So to do that, we just do shift right arithmetic. Sorry, not arithmetic. Shift right logical 3 times. So in the same way that shifting left multiplies it by 2, shifting right divides by 2. So that's divide by 2, divide by 4, divide by 8. So now we've got which row the ball is at. And this isn't going to be quite right. We're going to need to do some adjustment for the fact that the ball's Y position is offset by 16, and that's the top left. And then also we want to get the center of the ball. And then also another thing to think about is that we start drawing the stage map not on the first row of the screen, but actually a couple of rows in. So that's another thing to worry about. But I'm just also not going to worry about those things right now. We will need to fix it. So we divide by 8, and then we're going to swap it to multiply it by 16 to get the index into the stage map. We load that into L. So now HL now contains a pointer to roughly, not actually correctly, the tile that the ball is on. And then we are going to figure out what that tile is. And if it's not 0, if it's 0, we're going to say no collision. And if it is 0, I'm going to crash the game board. I think that works. I don't even know. I don't even know if there's a way out of the stop instruction. And I don't know if you need to disable interrupts, but hell, whatever. Let's fry the CPU while we do it. So this isn't correct, but it's vaguely in the direction of correct. It's got a few other problems too. Like if the ball is in the top left, we're just going to be poking at nothing. Yeah, it's just that okay. So it didn't work. Did not work at all. Oh, and we're not accounting for X either. That's another thing that I forgot to do. So that gets the row, and then we need to get the column. And the column, we don't need to do that multiplication by 16, but we do still need to divide by 8. And again, I haven't done some proper adjustments that I need to do, but nevertheless, I'm actually surprised that works. Do I export the stage map? Did I have that? I did have the foresight to do that. So then we're going to just add that to L and then do that again. So still not going to work at all, but I'm probably still going to just yell at me about accessing image ledger. So you can see we're trying to access tile EC, which is just complete nonsense. Actually, for the heck of it, show you how this is done. I'm going to set a breakpoint here, hit reset, and then fire this off. So we're going to get the ball's Y position, which we think is 76 in hex. Which, yeah, checks out. But actually on screen, I mean, I don't have an easy way to show that, to show exactly what the position is, but 76 is off a little bit. So then we're going to shift it right a few times, and we get down to OE 15. Ugh. Which, if we look at the map, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You can see that is roughly correct. It's not actually correct for a couple of reasons, but it is roughly correct. And then we are going to swap A, and so that puts the E up here. That multiplies it by 15. So that should roughly get which entry in the map is at the beginning of the row. And then we store that into L. So, and then we're going to get the X coordinate and do something kind of vaguely similar. But of course, this is completely wrong. It's out of bounds. So to fix this, we need to do a couple of things. First of all, we need to account for the fact that even if the ball were right at the very top of the screen, that wouldn't be at 0, that would be at 16. So we need to subtract 16 from that. But then also, we want to get the center of the ball, not the top left of the ball. So to that, we want to add 4. So really, we're going to be subtracting 12. To make this clearer, I'm going to say add 4 minus 16. I'm going to say like account for OM Y offset plus ball center. And then also what I want to do is I want to account for the fact that we actually start drawing the map at what did I say we would start drawing the map at? I said we'd start drawing the map at 42. So two rows in. So if it's up here or here, we should just break out early. Oh, what's the best way to do that? Maybe I don't want to just break it early. Maybe what I want to do is let it wrap around, so then we only need to check to see if it's out of bounds on one end. So then I'm going to actually end up subtracting another 16 to account for the fact that we are... yeah, let me try that. I'm going to subtract for another 16. And we have to do something similar here. We're going to add 4 to get the center of the ball. We're going to get minus 8 to account for the OAM X offset. And we are going to get, we start drawing this 2 tiles in as well, right? Yeah, so, and then plus another, or minus another 16 to account for ball center, OAM X offset, start. Well, let me actually, Okay. Yeah, actually, I think the easiest thing to do is to do this math here, and then because we have to do it for both. So I'm going to then compare what I just computed, the row number. I'm going to do this. So I want to make sure that the row number is somewhere between 0 and, I said it would be 8 rows. So 0 and 7, I'm going to compare it to 8. So if there's no carry, I just return right away. So if we're 8 or 9 or 10, this is going to subtract 8. It's not actually going to write the subtraction back into the accumulator, but it's going to subtract 8. And if we didn't wrap around, that means that we are 8 or greater, and we want to get out of here. And we're going to do something like really similar. Right over here. Yeah, I'm going to do that. Sorry, I got a little hung up on something I didn't need to get hung up on. And we're going to do something similar with the column. We're going to make sure that the column is somewhere between 0 and 16. And again, same deal, return if it's not. This Lord help me, I believe should be correct. I should roughly approximate, like, oh, sorry, I still have that breakpoint set. It's not, though. It's not correct. It's just bouncing. It's just ignoring everything. Oh, there we go. I finally hit the breakpoint. But, yeah, it's not great at all. Oh, I want to add 16 here. I want to add for the... I believe... Right, so if the ball's position is... Now I do want to subtract. If the ball's position is 16, then I want to be treating it as though it were 0. Well, now here's where things get juicy, I guess. Let me reflect on this for a moment. This feels okay to me. Oh, it's because I had already done the swap. Here's the problem. I just kind of like grouping all of the get row offset stuff together and then checking for bounds. Maybe that's dumb. That might be dumb. I think this should fix that. Yeah, there we go. Look at that. That is exactly what I wanted. Let's see if I can point this. You can see, yeah, perfect. So it crashes as soon as it collides with the background. Obviously not ideal. In fact, so not ideal that I'm going to I'm going to change this behavior. I'm going to, as I call it, reflect ball velocity y, and then return. This will seem a little bit more compelling, actually, I think. Maybe not. It's definitely doing some interesting stuff. Oh, the problem is that it's not getting pushed out properly of the tiles that it's hitting. That's what's going wrong here, and that'll be less of an issue because it's going to destroy the tiles that it hits. Once we get that implemented. But for now, I don't know. For now, this is pretty good, I think. I'm happy with this for today. We've made some serious progress here. We've got the new you can move quickly functionality. We've got this better input system which can handle a distinction between a key being down and a key being pressed. And oh, that's a bug. That's a bug that I need to fix. If you're moving to the right and you shoot the ball, it goes off to the left. Make note of that too, for something to fix. But we've got a paddle moving around faster. We've got better input system. We've got a background that we're drawing and a background that we're colliding with. So a ton of progress today. I apologize. I made some lapses in logic because I'm tired. That's my excuse anyways. I may have rambled a little bit because I'm tired. Again, that's my excuse. But on the whole, pretty happy with how this went today. Thank you for joining me. I'm going to continue this tomorrow. We're going to figure out what's going on with that bug where the ball goes shooting off below you. If you're moving it quickly, does it happen only when you're moving? It only happens when you're moving quickly, I think. Or at least only noticeably that way. We're going to fix that bug. We're going to get the bricks blowing up when you hit them. It's going to be spectacular. I can't wait. Have a good day. Enjoy your Wednesday. Take it easy. I'm out.